We're going to dive into the fundamental theorem of calculus, which connects derivative calculus with integral calculus. Here's where we are, just a couple of weeks left. So basically what the fundamental theorem of calculus says, and by the way, there's part 1 and part 2. Part 1 is a little more twisted and not quite as intuitive, but we'll work through it and we'll see what it's like. Okay, so the fundamental theorem of calculus establishes a connection between differential calculus and integral calculus. Remember we said that those two branches of calculus were developed at two different times by two different people, but it turns out that they are related in a very interesting way. The integral function is an antiderivative. So this g of x is equal to the definite integral of f of x dx. G of x is actually the antiderivative of f of x. So to find the integral, you would find the antiderivative of f of x. And you already know how to find antiderivatives, so you know that operation already. Now there's a little bit more to it to find the actual definite integral, because we have to take into account the boundaries, the lower and upper bounds, but we're going to go more into that in part 2. All right, now here comes a slightly twisted part. If you take the derivative, basically just think of you're taking the derivative of both sides of this equation. Okay, so you're taking the derivative of both sides of the equation. You're taking the derivative of g, which is the antiderivative of x. You're basically taking the derivative of the integral. And so since these two operations of taking the derivative and taking the integral are really inverses of each other, they cancel each other out. So what you get back is the function itself, the integrand itself, f of x. All right, so part 1 makes things a little bit more complicated. We still are looking at the definite integral. So first of all, there's some things that have to happen. We have to be continuous on an interval from a to b. And what we're going to do is look at the area under the curve in that interval, but not the whole interval. We're picking some variable place x in that interval, and we're only going to take the area up to that point. So this makes things, it sort of adds like an extra layer of complication on top of everything. Now we have to have a continuous function, we have to have a differentiable function, and so the derivative of g prime of x is equal to f of x, and that's just exactly what we looked at in the previous slide. So the derivative, all right, so let's put our arrows in here. So the derivative of the integral is the function itself, and again, we looked at that. We just looked at that in the previous slide, and now I'm just giving you a visual of what it looks like in terms of area. If you look at that vertical line that's drawn from x, looking at the graph, up to the curve, and think about sliding that line to the left, so we'd get less of an area, our area would be smaller, or sliding it to the right, we'd get a larger area. We just don't know where it is, so we're saying that our upper boundary is variable, and depending on where it ends up, it's going to make a difference to the area. So the fundamental theorem of calculus says, well, if you don't know what the upper boundary is, and again, you got to have a fixed lower boundary. Something's got to be fixed. So we got a fixed lower boundary, we've got a variable upper boundary. So how do you deal with that? Okay, so we're always going to integrate at the upper limit. We're always assuming that that upper limit is going to be the one that's variable. When we get to part 2, we're going to look at the lower and the upper being fixed. Much easier to deal with. But right now, the upper boundary is variable. Okay, so there's a lot of properties of the definite integral, and the one that we're going to use in this next example, in one of the parts of the next example, is just this first property, which says that the integral from a to b is the negative of the integral from b to a. So if you swap the upper and the lower limits, you simply get the negative of what you had before.